This is Bio 181, Chapter 3, Key Concept on the macromolecule, the group of lipids. So this one does not have true monomers or polymers. It's a very diverse group of molecules. What they have in common is that they are all not soluble in water, so they do not dissolve in water. That's a consequence of the fact that they're nonpolar. They function many different types of capacities. I'd like you to know that they function in energy storage. This is going to be long-term energy storage. In animal, the molecule in all your fat cells is a triglyceride. They also form the primary component of a cell membrane structure. So around every cell, primarily composed of phospholipids. So lipid indicates it's a lipid in the word, and phospho indicates it has a phosphate group. So if you remember your functional groups, that's PO4 with the -2 charge. They also function in cell signaling. Specifically, if you see the word steroid in front of hormone, that's going to indicate that it's a lipid. And again, it's going to indicate that it's non-polar. Later, that's going to be really important because it's going to allow it to go through a non-polar cell membrane and diffuse right into the cell. Okay, so they're non-polar. I keep saying that. That means that they are sharing the electrons equally. Most of the bonds are between a carbon and a hydrogen. This is a covalent bond. It's a non-polar covalent bond. So if you remember what that means, it means the electrons are shared equally. So they're going to be, there's a pair of electrons that are going to go around the carbon, around the hydrogen equally. So there's no uneven distribution of charge. So it's basically neutral. Neutral. Now, if water's over here, water, H2O, so I've got two hydrogens, 1, 2, and an oxygen. Remember that the oxygen is a little bit electronegative and the hydrogen is a little bit electropositive. So it has a partial charge. So this is not interested in this molecule here. So it doesn't care. Water is not attracted to something that's neutral. Instead, water is going to be attracted through hydrogen bonding to other polar molecules, like other water molecules, right? So that's where the water is going to hang out. And that's responsible for things like surface tension, right, that we learned before. So water is going to want to bond to other polar molecules. It'll also dissolve things like if there's a chloride ion, it's going to be attracted to that, right? So that's going to be attracted. It's going to surround it. It's going to exclude this. So if you have a glass of water and you have water in it, and you add, let's say we add a fat, I'm going to add a lipid. So an example of a lipid would be an oil, like olive oil. If we pour olive oil on here, it's not going to mix. It's just going to be on top of the water because it happens to be less dense. So it's not soluble. All right, let's go through a few examples. So fats are a type of lipid, and the molecular structure of fats, we have what's called a glycerol and some fatty acids. So for the glycerol, hold on one moment. All right, so for the glycerol, we've got I'm just going to write it over here. I'm not going to worry about the structure right now. So the glycerol is over here. It has some OHs on it. It's an alcohol. You can see the OH on the end. But basically, it's a unit that is composed of carbon and some oxygen, hydrogen. And that's going to be bonded to a fatty acid. And a fatty acid is a sequence of molecules, a lot of hydrocarbons. So we have hydrocarbon, And it's going to be just bonded to more carbons and more carbons. Each carbon is going to be bonded to 4 other molecules. And eventually you'll get to a point where at the end, this carbon is bonded to a carbon that's double bonded to an oxygen, and then it's bonded to an OH, a hydroxyl group. So again, carbon makes 4 bonds, so we're good. 1, 2, 3, 4. This molecule on the end, it has a characteristic. This is a carboxyl group, so it's actually going to be acidic. And so this hydrogen will often pop off, increasing the acidity of the solution, which is why it's called a fatty acid. So together, a glycerol and a fatty acid together, these two together, you can make a fat. So let's look at an example of that. Okay, so here, we've got a saturated fat. You can see there's lots of hydrocarbon bonds. So most of the bonds in this molecule are these non-polar covalent bonds. So that means this whole section here is neutral, right? And so it's hydrophobic. So that makes the whole molecule pretty much hydrophobic. This end is a little bit polar, but you don't have to worry about that because it's way outweighed by the fact that most of the molecule is hydrophobic. So over here on this end, again, you can see this hydrogen will often want to, it's loosely held to this oxygen. This oxygen is a little negative, and so it will often go into solution, which makes this an acid. So this is a saturated fat, and what that means is that there's no carbon-carbon double bonds. So if you look at all the bonds between, I'm just going to pick here one here on the right, this carbon-carbon bond, there's just one single covalent bond, one line linking it together. So this molecule is going to actually be a pretty straight molecule, and they can pack together with other molecules very easily, makes more rigid structure. Saturated fats tend to be not soluble, they tend to be a solid at room temperature, okay, like butter. So that's in contrast to an unsaturated fatty acid. So unsaturated, this looks very similar to the last slide, except that we have a double bond between one of the carbons. You can see right here, there's a double bond. That means that they're sharing 2 sets of electrons between them instead of just one pair. And what happens though is that this is going to cause a structural change where there's a kink. So instead of being just straight, it's now has a kink in it. And these do not line up very easily with other ones. And so they're actually going to be much more mobile in solution, and they'll be a liquid at room temperature. So a liquid at room temperature, so things like oil, as opposed to a saturated fat. So like olive oil is an unsaturated fatty acid. If you have multiple double carbon bonds, then it's polyunsaturated. Okay, a triglyceride is fat storage in an animal. So the primary molecule that is fat, if you go to the doctor, they're probably going to check your triglyceride levels, right? You don't want them too high. So triglyceride, we've got a glycerol plus 3 fatty acids, and then we get a triglyceride. So basically what that is often going to be represented. You're going to have the glycerol up here. The fatty acids are going to look kind of like this. And you might say, well, what does this represent? Good question. So this is the glycerol on top. Each of these vertices is a carbon. And the carbon is bonded to another carbon. That's all that we're looking at. In fact, there's going to be hydrogen bonded to these carbons as well. So if we were to draw it, I'm just going to draw the right one. This is what it would look like with all the bonds. But it gets pretty messy. And so to simplify it, to leave off all of the C's and H's and just have this backbone that is this zigzaggy line. All right. So if we had another one here, we would have 3 fatty acids linked to a glycerol. That would be a triglyceride. Okay, a phospholipid is the primary component in a cell membrane. We'll go into this in more detail when we look at cell structure, but I wanted to bring it in now. So, and just so you remember, we learned these functional groups. Up here, there is a phosphate group. And that's going to be bonded to 2 fatty acids. This. Okay. And the phosphate group, remember, is PO4 minus. So in a phospholipid, we're actually going to have a head that is charged or polar. Okay, so we have an uneven distribution of charge up here. Still, the vast majority of the molecule is going to be neutral. But in a phospholipid, we do have one end that has a little bit of polarity. That's going to be really important for how it interacts with other molecules. The last example is a steroid. I won't say much about these. Steroids are hormone signaling molecules often, and things like estrogen or testosterone, those are steroids, and they're actually these ring structures, and there are going to be multiple ring structures put together. So for estrogen, we have a double bond there, and we have too much about getting this right, but it's basically 4 ring structures, and the pentos here. So again, each of these vertices is a carbon. These are covalent bonds bonding them together. You're not seeing the hydrogens, but if we were to put hydrogens in, you would say, okay, this carbon over here, this one over here, it already has 2 bonds, 1, 2, and so it actually has 2 hydrogens that are attached to it if you were to look at it. But that's kind of messy again, so we just draw the 4 ring structures. And I think that, yep, that's it for the lipid video.